Awesome. Welcome back. This is the fourth video in our series here, and I want to talk to you about a game that I really love. It's called Set. So it's a deck of 81 cards, and each card is defined by four properties. Each card is defined by a shape that the card has, by a color, by a shade, and by a number. Okay, so the shape of the card of the objects in the card can be oval, diamond, or squiggly. For instance, here's an oval, here's a squiggly, and here is a card with diamonds. A card can have three colors: green, red, or purple. So you can see the different colors around. The objects can have different backgrounds, different shading, solid, empty, or sort of like partially shaded. And then the card can have the numbers 1, 2, or 3 objects. So for instance, this is 1, this is 2, and this has 3 objects. So every card has to have a shape, a color, a shading, and a number. So there are 3 options for each. So 3 times 3 times 3 times 3, that's the 81. That's why there are 81 cards. And the purpose of the game is you lay down 12 cards, and players sort of like sit around a table and they look at the 12 cards and they want to find what it's called a set. And a set is a collection of 3 cards that satisfies the following property. So when you consider the 3 cards and you look at their shapes, either the 3 cards have to have the same shape, that is, all 3 of them have ovals, or 3 of them have diamonds, or all 3 of them has squiggly, or they have different shapes. So 1 oval, 1 diamond, 1 squiggly. And the same has to be true for the color, for the shading, and for the number. Okay. So they have to have same color or different color, all the same shading or all different shading, all the same number, and all different numbers. And I'm going to show you some examples in a moment, but here is actually a collection of 3 cards that forms a set, because for instance, if you look at the number of objects, the bottom one card has 1, the other one has 2, the third one has 3, so they're all different. And in this one, actually, if you go through so this doesn't look like, but this is partially shaded, that's why it almost looks like it's empty shaded, but it is partially shaded. So when you look at the shading, fully shaded, partially shaded, and empty. So they're all different. And it all works out. So you can check the other 2 properties. This 3 cards here lined up, they don't form a set. And let me actually go through a little bit of why they don't form a set, because they almost form a set. In terms of colors, they all have different colors. In terms of shading, they all have the same shading, which is completely shaded. That's good. In terms of shapes, they all have different shapes. That's also good. However, the issue that they have is in the number. So in this one, you have 1 card, 1 object, 1 object, and 3 objects. So it's not true that they're all different, because these 2 share the fact that they have 1 object. So the third one actually had to have 1 object if it was going to work. So if you actually had the 1 purple fully shaded diamond, that will have been a set, but it's not. So hopefully you get the hang of it. Here's a few more examples. This is a set. All of them have 1 object. All of them are fully shaded. They have different colors and they have the same shape. So that works out. This one also works out. You can check. And this one, all of the properties are different. And this is another non-example. And this one doesn't work for several reasons. One of them is you have 2 red cards. So 2 of them share a color. The third one should have been a red if this was going to work. And another property that doesn't work is shading. So these 2 are fully shaded. This should have been fully shaded. Shapes, these 2 are ovals and this one is not. So there are a lot of ways in which this fails to be a set. And the idea is players start grabbing sets, and if someone grabs a set, you put 3 more cards, and if someone grabs a set, you put 3 more cards. and the game goes along until you have no more cards and there are no more sets on the table, and you count how many sets you got. And it's a super addicting game. So if you haven't played it, I really suggest you do. Okay, it's an awesome game. Okay, now let me answer sort of like a combinatorial question about this. How many total sets are there? So how many sets are there in this deck? So let's think about the following. Imagine that I give you two cards, any two cards. So I just picked these two, but it could be any two cards, okay? If I give you two cards, can you find a third one, or how many can you find that forms a set with these two cards? And that's an interesting question because we can actually check. So let's see, this card is red, this one is purple. So they don't share a color. The third one cannot share a color, so it has to be green. This one has one object, three objects, the other one has to have two objects. This one is fully shaded, this one is partially shaded, the third one has to be empty. This and then what is the next property? The shape. Oval, diamond, this one has to be a squiggly. So in fact, this is the only third card. This is the only card that forms a set with the red and the red one oval and the three partially shaded purple diamonds. This is the only card that forms a set. So given any two cards, there is a unique third one that forms a set. That's a key property. Given any two cards, there's a unique third one that forms a set with those. And with that, we can count how many total sets are there, because you have 81 cards, and out of the 81 cards, you can choose any two of them, right? So 81, choose any two of them. There are 81 times 80 divided by 2 ways in which you can choose two cards out of 81. And then for any of those choices, you're going to find a set. Now we have to be a little bit, well, and the set is, well, you get the third card that forms a set with those two, and that's how you form the set. We have to be a little bit careful because we're double counting. For instance, if I grab these two cards initially, then I know that this third one is the one that forms a set. But if I had grabbed these two instead, then the third one that forms a set is this red one, and it's still the same set. So I'm double counting that set. And if I had initially grabbed the first card and the third one here, then the other one that forms a set is the middle one. So I will be double counting this one again. So in all the possible ways in which you can choose two cards, you will be double counting. Okay. So what you do is you get rid of the double count, and what you get is that there is 1,080 sets. Okay, that's the total number of sets in the deck. Now, what I want to do now is I want to define an operation on the set of cards. Okay, so just like in abstract algebra, for instance, you describe operations like addition of integers, multiplication of integers, multiplication of real numbers, addition of real numbers, composition of functions, composition of symmetries in the symmetric group or in dihedral groups, and so on and so forth. You study many different operations. I'm going to define an operation on the deck of cards. And the operation, I'm going to just show you an example in here, but you'll get the essence of it is, given any one card and any second card, I'm going to operate on them. I'm going to use the symbol star, because frankly you can use any symbol. And I'm going to set that operation to be equal to the third card that forms the set. Okay. And this actually works just as well defined. There's only one caveat, which is, what if it's the same card star the same card, and we define that to be the same card again. But other than that, including that, this is a well-defined operation. One can check. There is no ambiguity. And given any two cards, their star operation is going to be the third card that forms the set with those two. Okay, and it's quite interesting to study this operation. One can say, well, take the set of cards with this operation. Does it form a group? You can think about it. The answer is no. There is actually no identity element. But it's still quite interesting to study this object with this set with this operation, because you still have things like, this operation is commutative, because if you take these two cards, really it doesn't matter in which order you took them. The product is going to be the third card that forms the set with them. It satisfies left and right cancellation laws, one can check. It doesn't satisfy associativity, but it does satisfy sort of like a different type of property that it's not associativity, but it has to do with sort of like what happens as you do as you shift certain operations. So at the end, what this structure is called is a quandle, and quandles appear also in knot theory. So it's sort of like it's still a structure, and there's tons of things to say about it. So this is a quite interesting project to study. What I want to do with this operation is actually answer a different question, which is, or at least give a bound. I won't be able to give you the full answer, not with this approach, but it's a really, really interesting question, and it is, if you have the whole deck, 81 cards, and you're playing, you put 12. The rules are you put 12 cards on the table, and there is actually a chance that there might be actually no sets in those 12 cards. And what the dealer does is, what the players do is they put 3 more cards. So you have 15 cards in the table, and hopefully you find a set, but maybe not. Maybe you put 3 more, and maybe you continue. At what point do you guarantee that there has to be a set? So for instance, if all 81 cards are on the table, I can tell you there is a set. It's easy. You can find 3 cards to form a set. But what is that threshold limit? If that once you have that many cards, you're guaranteed to have a set. And that is an interesting question that has been answered, but it can be generalized to, this question can be generalized sort of like to any dimensions. So you can imagine cards that instead of just 4 properties have 5, maybe a background, an odor, or something else. So you have 6, 7 different properties. And in general, if you have n properties and 3 options for each, it's not known what is the minimum number of cards that will guarantee the presence of a set. In fact, Terence Tao, which is who's one of the greatest mathematicians alive, has called this his favorite open problem. And there are more things. In 2016, there was a breakthrough of how large can this number be. So we know some things, but in general, I think we know the answers up to the 6th dimension. If you have 6 properties, once you go to a 7th one, we don't know what the answer is. But one can study this problem in this setting, in the setting of the game set, just with these 4 properties, with abstract algebra and with this operation. We won't be able to give the final answer, but we will be able to get a bound. So, and it's actually a quite simple argument that I'll explain in 3 or 4 minutes right now. So this is how it goes. Imagine that you have n cards that don't have a set. So I don't know, just in general for any n. Okay, so I have a set of n cards that don't form a set, and I threw in a picture there, just for you to remember that there are n cards in this bubble, which is a set. It's a collection of cards. It doesn't have a set in the sense of the game. And let's say that I choose one card from those n ones. It doesn't matter which one. So let's say that it was this one. Okay, this is what I'm going to do with that card. I'm going to create a second collection of cards. And the way that I'm going to create it, and I'm using this notation, which is a slightly abusive notation, is I'm going to take all the n cards in this set, in this collection of cards, all of the n ones, and I'm going to star them with this chosen card that I chose. Okay, so I'm going to star them, and remember, the star is the operation where if I take this one red filled oval times, I don't know, these 2 empty squiggles red, when I start this one times the 2 squiggles empty red, I'm going to get, in this other collection of cards, I'm going to get a 3 oval partially shaded red. That's the third one that forms the set. So that will be here. So I do that for all of the n cards, and I'm going to get n cards again in this other set. I am going to have this card again, because when I star that card with itself, I get itself. So I'm going to get that card. But one can actually show that when I do this thing, other than this card in the middle, there is no other intersection between these 2 collections of cards. Okay, so if you start with n cards that don't have a set, choose one, take that one, star all of the other ones, and you collect what you get. One can show that actually the intersection is just one card. Okay, and that at least says something. It says this n cannot be 41, for instance, because if I have 41 cards here, well, actually it could be 41, but it cannot be 42. If I have 42 cards here, right, that don't have a set, when I start all of those 42 with this one, I'm going to get 42 new cards here that don't have a set, that collection, and that the only intersection between the two sets is this one. But that will imply that I have 42 plus 41 cards, which is 83, and that's more than the number of cards we have. But that's actually too high of a bound. We're going to push it down a little bit more. Okay, so this is what we're going to do. Out of the n cards that we have here in this collection of cards, if I choose any two of them, I will be able to create a set with. I'll be able to find a third card that forms a set with those two. So I'm going to do that. I'm going to take from all of these n cards, and I'm going to find all possible ways in which I can choose two of them, and I'm going to create this many sets, n times n minus 1 over 2. That is n choose 2. If you have n cards, you have that many ways of choosing two of them. And for each of those choices, one can show that you find a third card that forms a set, and you have that many unique sets, okay, different sets. Okay, I can do the same thing with the cards on the right bubble here. Now, I'm not going to use this one anymore because I use this one in this n choose 2. So what I'm going to do is I'm going to take the other n minus 1 in this bubble that are not this one fully shaded red oval, and if I choose any two of them, I can find a third one that's going to form a set with those two, and I can see in there n minus 1 choose 2 such sets. That's how many there are, and it's not actually too hard looking at the problem and thinking about it for a few minutes to show that these are actually going to be disjoint, because if you choose two cards from here, those two cards already will be different from the two cards that I choose from here, because I'm choosing from the part that's not intersected with the left bubble. So these two cards that I choose on the left hand side will be different than the ones that I choose on the right hand side. So already those sets will be distinct. Okay, so this many sets, you can find this many sets that are distinct. Okay, but we know how many total sets are there. There are a total of 1,080 sets. So if you actually create this inequality that the number of sets I form like this plus the number of sets I form like this, that has to be less than or equal to 1,080, you're going to get that n has to be less than 34. Okay, so that says that if you have 34 cards, you're guaranteed to have a set. Okay, so and it's a short argument that only uses a little bit of abstract algebra and combinatorics and thinking, and sort of like doing some clever constructions in here. Now, the actual bound is 21. If you have 21 cards, you're guaranteed to have a set. So 20 is the largest collection of cards that you can have without a set. But it's still quite interesting that that with a little bit of abstract algebra, you can bring this bound down to 33 actually, well 34. That once you have 34, you have a set. So I find that quite interesting, and it's such a joy to use a little bit of abstract algebra to study this game. Okay, so thank you so much for listening to this presentation. I do want to throw in a little bit more about a few other games like Bingo. I have Bingo in here. So recently there was an article that said the following, or it showed the following, or it discussed the following question: if you're playing Bingo, what's more likely? Is it more likely that you're going to win with a horizontal row or with a vertical row? And if you haven't played Bingo, you can look up the rules of the game. I'm not going to say too much about it, but I think that's an interesting question. A Bingo is a 5x5 sort of like cardboard. You can win diagonally, vertical, or horizontal, but the question is, are you more likely to win horizontal versus vertical? And I guess what most people might say is, well, it should be 50-50, it's a square, there may be symmetry arguments, but it's actually not. So I'll leave it up there. If you wanna know more, Google that question about Bingo. And there are tons of other games, tons of other Rubik's-like puzzles, there's a game called Spotted, which has to do with a deck of cards. Even games that are well known, like poker and blackjack and things like that. There are interesting mathematics to explore in all of these games. So I hope that by watching these videos, you have gained a sense, you have seen that mathematics can be used to explore games in a joyful way, but that still involves sort of like interesting and interesting mathematics, not trivial at all. So, for instance, in the Rubik's Cube, it's not trivial at all to have solved the questions that we solved. So I hope that you enjoyed the presentations, that you realize that you can use mathematics to have joyful experiences with games. It has been my absolute pleasure. I'm going to have another video, the very last one, where I talk about my story, how I came in to be a mathematician, and a few other things. So stay along for that last video. I hope you're enjoying this, and see you in the next one.